Okay, so we're running a little bit late. Sorry about that, everybody. Just some technical difficulties. But welcome to our next session. My name is Jim Way. I'm Executive Director of the American Astronautical Society, your host for this event in conjunction with NASA Goddard and all of our sponsors. So let's get started with this session. Earlier this year, the National Academy of Sciences released a report titled Reflecting Sunlight: Recommendations for Solar Geoengineering Research and Research Governance. Is geoengineering a realistic approach? Considering this report and other data available, what other options do we have? So this session, generously supported by Teledyne Brown Engineering, will look towards climate solutions from needs-driven observations to solar geoengineering research. Our panel will discuss potential mitigation strategies and their predicted impacts. Our moderator today is Danielle Wood, Director of the Space Enables Research Group at the MIT Media Lab. So Danielle, welcome and take it away.
Thank you so much, Jim, and welcome everyone. As you heard, my name is Danielle Wood, and I'm so glad to spend this time with you today. Thank you for joining us in this session entitled Towards Climate Solutions: From Needs-Driven Observations to Solar Geoengineering Research. It's wonderful to have several panelists with us today, and I'll introduce them briefly and refer you to the online information for their full bios. We'll hear today from Dr. Raha Hakimdavar, Director of Space Sciences, Fall Aerospace; Dr. David Keith, Professor of Applied Sciences at the Harvard School of Engineering and Applied Sciences, as well as Professor of Public Policy at Harvard Kennedy School; Dr. Kate Ricke, Assistant Professor at the School of Global Policy and Strategy, as well as the Scripps Institution of Oceanography at the UC San Diego, University of California, San Diego; and finally, Dr. J.P. Walsh, Director of the Coastal Research Center and Professor in the Graduate School of Oceanography at the University of Rhode Island. As we host this discussion, we're going to build on the previous conversations held here in this venue on the questions of the role of space in our organizations to respond to climate change. The earlier sessions particularly highlighted opportunities to use measurements from space to understand and assess climate change and to turn that information into decision-based information. Today, we'll highlight two kinds of responses to climate change, both adaptation and mitigation, with a heavy focus on the topic of mitigation. But let me define, according to the climate.nasa.gov website, these two terms as a foundation for our discussion. Now, climate mitigation refers to reducing emissions and stabilizing the levels of heat-trapping greenhouse gases in the atmosphere. In contrast, climate adaptation looks at the climate change that's already taking place or it's already in the pipeline and changing the way we live to respond. I read some examples in preparation for today's discussion from NASA, from the Global Environmental Facility, and from the World Resources Institute to see what kind of activities are recommended for climate mitigation and adaptation. And ideally, some of these activities actually achieve both at the same time. Work on sustainable cities, increasing examples of low carbon technology, making buildings more energy efficient, and implementing renewable energy. These are all some things recommended, including also in another category, the idea of changing our food systems, our land use, and pursuing land restoration. Trying to find ways to increase the benefits of coastal wetlands, especially mangrove forests, as well as implementing more mass transit systems. Also, there are ideas around increasing agroforestry, so the mixing of hosting forests alongside agricultural land, and considering how trees can play a role alongside crops and livestock. These are all well-documented suggestions about ways to both mitigate the future emissions of greenhouse gases, as well as adapting our current lifestyles. As we consider this, let's also consider what are more radical ways to perhaps directly address the issue of the presence of greenhouse gases. And here we can consider two known fields of work, one in the category of carbon removal and one in the category of solar geoengineering. We'll speak today particularly about solar geoengineering, responding to, as you recently heard, the release of the National Academy's report called Reflecting Sunlight: Recommendations for Solar Geoengineering Research and Research Governance. So we're thankful today to have with us a representative from the committee, Dr. Kate Ricke, and a known expert in the field, Dr. David Keith. So we'll have extra time for discussing those particular examples of mitigation. As we lead into that discussion, I first would love to have a conversation starting with Dr. Walsh and think about what is the motivation for emphasizing mitigation, even as climate adaptation is already happening. Dr. Walsh, you work with coastal communities around the world. You also live in a coastal community, and you are regularly seeing the impacts of climate change, both in your own region, but also in regions where you study, especially near the equator. Many of these communities are already implementing climate adaptation strategies, and you see the challenges they face in the economic and social level. Considering your experience, and also considering kind of the broader ocean health, why is mitigation so important for us to consider, even as we work on adaptation? Thank you. Please go ahead. You have about 5 minutes.
Thanks, Danielle. And hello to the panel and the audience. It's a pleasure to be here for this important conversation. First, of course, climate change is happening and it's manifesting itself in many ways that have real consequences for communities and countries. And our work of the Coastal Resources Center at URI and with our partners locally and globally focuses on coastal and ocean issues like sustaining seafood and managing shorelines and seas. Unfortunately, adaptation options are limited and have trade-offs and also have significant costs. So decision-making is hard and financing must be sorted out. It's not an easy thing for communities to fund adaptations in many ways. We encourage inclusive and transparent processes for decision-making. But of course, these challenges are difficult, requiring time and money. Also, the physical and socioeconomic landscape and the policies themselves for managing these areas are evolving with the climate. In many areas, populations and development are growing. Resources are critical ones are relied upon, such as fisheries, are limiting. So communities face real tough decisions. Adaptation can take many forms, and I know we won't talk a lot about adaptation today, but I want us to, it may come up in the conversation. Adaptation, like elevating or helping nature in different ways, resisting, building hard or soft structures, or retreating is another option. Mitigation is critical for us to consider as it can help us limit the magnitude and the speed at which climate change happens, and thus the speed at which decisions and investments need to be made. These are tough issues. Also, mitigation investments such as things like mangrove protection or planting, guided by remote sensing, may help communities with protection against flooding and provide other important ecosystem services and benefits. So those are just some of the thoughts that I want to begin with to start off the conversation.
Thank you so much. We'll certainly hear more from you as we kind of converse with the other speakers. And let me turn next to Dr. Hakimdavar. You represent a company that works closely with NASA and other US government missions. And often Ball Aerospace is playing a role in producing the sensors and systems to make observations. And you may be observing activities or helping support activities that are working toward climate adaptation and mitigation, such as those I mentioned earlier. Your company also is very conscious of your broader impacts and sustainability. Can you comment, please, on what you see the role of the private sector in supporting the kinds of science that will guide climate responses?
Yeah, thank you for the question and for that great introduction. So I guess I'll start out pointing to my own background that I spent a considerable amount of time actually working on the adaptation side with the U.S. Forest Service, with the United Nations and with the World Bank, but I have also been on kind of the research and now on this, on the private or the industry side. So I would say that the short and very simple answer to that question is really collaboration. And of course, the aerospace industry has been working with government agencies for decades to develop the surveying that have enabled us to understand changes in our land surface, our oceans, and our atmosphere. I really see the time now as being so exciting because we are finding so many uses and so many users for this sort of space-based data, which we heard yesterday. And it's really going beyond the science, and at times it's going beyond the original intention of our missions. So this connection between science and applications is really growing, and it's just an amazing time for us to together figure out how we can develop instruments that can meet more user needs in addressing the very important and outstanding science questions. So several of the speakers yesterday talked about the importance of observation longevity, continuity, and reliability. So I would first say that within industry, I think we should continue to support the science with our technology development, at the same time trying to meet the operational needs. And as much as we are serving as a mission partner, also serving as a science partner. And that's something that I think Ball has been really an advocate of, and really it's been very important to our work. So diving a little bit deeper into your question, I am going to quickly provide some specific examples and experiences from Ball. And I want to focus on the concept of collaborative constellations. So your question was really about the mitigation side. So on that, we've been part of a pretty unique partnership with the Environmental Defense Fund on MethaneSat. Cassie Eli from MethaneSat LLC spoke during a panel yesterday, so I won't go into too much of the details, but essentially MethaneSat spectrometer, which was designed and built by Ball, will provide a high resolution detection of and quantification of methane emissions around the world, and focusing on particular areas, especially oil and gas operations. So what's unique about MethaneSat is that unlike missions designed to locate super emitters, the MethaneSat instrument will provide accurate and quantifiable column measurements of methane concentrations over the target areas. So it's really going to fill a critical data and observing gap between the existing point source and the global mapping satellites. And this kind of information and this kind of data is really what's needed for successful greenhouse gas monitoring, policy, and regulation development. So we're really excited about that. And a second example is NASA's upcoming TEMPO mission to monitor air quality. So TEMPO is targeted at improving the monitoring, assessment, and chemical understanding of air quality over greater North America, from Mexico City, which is one of my favorite places in the world, and all the way to Canada and coast to coast. And so TEMPA's ultraviolet visible light spectrometer, which was built by Ball, will be able to observe a host of pollutants, including ozone, nitrogen, and sulfur dioxide, at much higher temporal and spatial resolutions than our existing satellites. And this, of course, has a potential to really improve our air quality forecasts, which in a real sense translates to being able to protect public health and safety. And what's really interesting here is that TEMPO has a sister satellite called GEMS, which was also developed by Ball along with the Korea Aerospace Research Institute, or KARI. So GEMS, which was launched actually earlier last year, will improve early warnings for dangerous pollution events across the Asia-Pacific region, but at the same time also help to monitor long-term climate change. So with TEMPO, GEMS, and also the European Space Agency's Sentinel-5P satellite, we have a pretty amazing perspective of air quality across the globe. And one third thing I do want to mention, Landsat, which has just given us such an amazing perspective of change over our planet since the 70s. And it's not only enabled amazing science, but provided key information to support our management and planning efforts. So Ball supported Landsat 8 and the upcoming Landsat 9 alongside NASA Goddard, and we designed and built the operational land imager. So the OLI, among its many other applications, has really significantly enhanced our ability to monitor water quality and map wetland space. So I'm a hydrologist, that is my background, and I have such a deep appreciation for this, given how limited ground-based water quality data are, and just how fragile our wetland areas are, and how important they are in the fight against climate change from multiple perspectives. And I would just note that the idea of collaborative constellations is a great way for us to leverage existing resources and provide the accurate, quantifiable global observations that can meet both the temporal and the geographical coverage, but can also include spatially and spectrally improved data, which is meeting the needs of our user communities, or those that are on the front lines of both adaptation and mitigation efforts. And just to note that this is actually something that the operational weather community has been doing for some time, and that's also an area where Ball has been quite active. So you did bring up the point about internal actions at Ball around sustainability, and what is very interesting is that Ball Aerospace, where I work, sits within Ball Corporation. And Ball Corporation is a global packaging company that has essentially developed its business model around sustainability, starting with those iconic glass mason jars with the Ball logo. And it's gone on to become the world's largest manufacturer of recyclable metal beverage and food containers. And that I think is something that is really important. And in a sense, a very, very small example of that in terms of a circular economy within the company is that all of the aluminum byproducts from the aerospace operations are recycled for use in packaging operations. So it's just a really elegant, beautiful closed loop system. And just going to wrap up and close by saying that, when I think about the challenges facing us with the climate crisis, I think about the fact that we have had more collaboration and treaties over transboundary waters than we have had conflict. And that's because I recognize how important water is to our survival, not just as individual nations or regions, but truly as a species. And I look to examples like this of successful collaboration as, I guess, or hopefully we all can look to these examples as our North Star to help us navigate through the big challenges that are facing us with climate change. I look forward to learning some additional perspectives from colleagues that will be speaking next, and really excited about the discussion at the end.
Thank you so much. I'm really appreciative of the way that you brought in some of the key points from earlier in the symposium, and reflecting on our first two comments that we've heard from Dr. Walsh and Dr. Hakimdavar, and I think we can learn some key themes. First, as we heard, coastal communities who are some of those facing the immediate impacts of climate change, they need time, meaning they have big decisions to make. I often work in communities in Indonesia and parts of West Africa and parts of South America, like in Brazil, and they're eager to, for example, help sustain wetland communities and mangrove forest. They're eager to think about when to retreat, when to reinforce those key examples of adaptation, but all the plans they have will take years to implement. And we basically would like to give them more time. We like to say, well, it'd be nice if you could have an extra 5 or 10 years to grow those trees and to implement the policies, and also to help people shift their daily routines so that there can be time to adapt successfully. And I think one of the themes you're hearing from this suite of discussions includes the need to be able to have multiple approaches to responding to climate change, which is why it's so timely to consider the recently released report called Reflecting Sunlight, Recommendations for Solar Geoengineering Research and Research Governance. We could look at the global community beyond the United States and say that there's been a call for exploration of what can be done with solar geoengineering. And of course, we can appreciate that researchers like Dr. Keith have been working on this for a long time and asking what are the opportunities and what are the questions we should ask. We are so privileged today to have someone with us who can bring us really the most recent discussions at the level of the national academies on this topic of what role solar geoengineering might play. In particular, it's defined here as the attempts to moderate warming by increasing the amount of sunlight that the atmosphere reflects back to space, or by reducing the trapping of outgoing thermal radiation. And of course, while we are definitely saying we'll have to continue to work on things on the side of mitigation on the ground, such as decentralizing power systems, increasing the use of low emissions power systems, making sure that our agriculture is, over time, more and more reduction of emissions. Are there questions also to explore with these other forms of mitigation? So I'd now like to introduce Dr. Kate Ricke, who played a role on the National Academy Committee, and will now present from the point of view of the committee some of the key findings of this recent report, Reflecting Sunlight, Recommendations for Solar Geoengineering Research and Research Governance. And we've paused to note that this is exciting in the sense that there are strong views on sort of both sides of the discussion, and the report has really come out to try to present the need for further research. So Dr. Kate, we're very happy to have you share the slides and highlight the perspective of the committee. Thank you so much.
Thank you so much for the opportunity to be here today to give you an overview of some of the key outcomes of the process of our 2-year study committee proposing a solar geoengineering research agenda and recommendations for governing that research. Is this I'm seeing the presenter view of the slides. Is this the right view of the slides that I should see? Okay. All right, great. Just to note that this was a consensus process, meaning that all of our 16 expert committee members had to agree on the details of the conclusions and the recommendations. And those are the conclusions and recommendations that I'm going to present to you today. Next slide, please. So as we've already heard, we're talking about this in the context of increasing climate change impacts. And next slide. This figure from the latest UNEP gap report illustrates the challenge here. So despite some real progress on policies to reduce greenhouse gas emissions, we're far off track for meeting the global temperature targets that are laid out in the Paris Climate Agreement at the moment. Next slide, please. So this is really the context increasing conversations about solar geoengineering are occurring within. Next slide, please. So what is solar geoengineering? These are proposed approaches that might moderate planetary warming by increasing the amount of sunlight that the atmosphere reflects back to space by reducing the trapping of outgoing thermal radiation. And this figure here shows the 3 types of solar geoengineering that our committee was tasked to assess. 2 of these, which are stratospheric aerosol injection and marine cloud brightening, exploit processes which reflect sunlight back to space before it can be absorbed by the Earth, while the 3rd, cirrus cloud thinning, targets clouds that have a warming effect on the planet. And so by thinning these, scientists believe that more thermal radiation emitted by the Earth could escape to space. Next slide. This is just to note that our report is building on a previous National Academies report. Next slide. And the new work that we were charged with was to explicitly recommend a transdisciplinary research agenda for these 3 forms of solar geoengineering I just introduced, to particularly consider its potential impacts on, for example, the climate and ecosystems, to recommend specific mechanisms for governing solar geoengineering research, and to consider our research agenda and that research governance in tandem, recognizing the necessary coupling between these 2 things. Next slide, please. Before we delve into the study outcomes, it's important to emphasize that the committee agreed to this early in the process, that a foundation for our entire thinking about the study is the recognition that solar geoengineering is a potential additional strategy for responding to risks of climate change, but is not a substitute for other approaches, in particular reducing emissions, because, for example, it does not address the root cause of climate change, and it raises concerns about new risks and uncertainties and unintentional or unintended impacts. Next slide, please. So as I mentioned, we examined these 3 approaches, and I just want to introduce them to you for those of you that might not be familiar with these technologies or proposed technologies. Stratospheric aerosol injection is the approach that's been studied most extensively thus far. And there's a confidence here that it could induce global scale cooling, which we know partially from observations of large volcanic eruptions as well as modeling. However, there are still many uncertainties about the injection processes and their effects, as well as the climate response to this approach. Next slide. We also have strong evidence that adding aerosols to marine clouds can increase their reflectivity, including observational evidence from ship tracks. But there's much less evidence about this technology, about whether it's scalable to produce actually global scale cooling. And our understanding is hindered by key uncertainties about cloud processes. Next slide. And then finally, cirrus cloud thinning is the approach that we looked at, that we understand the least about. The science on this technology, which has to do with, like I said, thinning clouds that have a warming effect on the climate, the science here is still nascent, and some of the modeling results are actually contradictory. Next slide. So as far as some of our key conclusions, from our assessment of the science, we concluded that integration across physical, social, and ethical research dimensions is needed in this area, and that the research about environmental and societal impacts is really in a nascent state. So we couldn't make any strong conclusions about the research in this area yet. Next slide. We also agreed that the goal of any coordinated research program in this area is to better characterize and reduce uncertainties concerning benefits and risks of solar geoengineering, specifically to inform decision-making, while still acknowledging that there's always going to be uncertainty about the effects of technologies like this, regardless of how much research we end up doing. Next slide. A key recommendation that we made is that the US should establish, in coordination with other countries, a transdisciplinary coordinated solar geoengineering research program, and that this program, while being a minor part of the overall US research program on climate change, should focus on developing policy relevant knowledge about solar geoengineering, not for advancing a path for deployment. Next slide. And we envision a research program that integrates three elements which interact with each other at every stage in the process. The three elements being the research governance, and public engagement activities. And we recommend the program be structured in a way that includes regular assessment and revision to the goals, as well as exit ramps for ending the research program, depending on what we learn. Next slide. Okay, finally, I'm going to give you an introductory overview of what the research agenda we propose is. So rather than organizing the research agenda around disciplinary fields of study, we propose 13 clusters of interdisciplinary research questions that target these decision-relevant uncertainties. So there's considerable linkages and overlaps among these clusters, but to make it easier to grasp, we've grouped them into these three broad categories. The first, which is this sort of tan box at the top of the diagram, is about context and goals. It's sort of an atypical research cluster in that it focuses on research which would improve the solar geoengineering research enterprise itself. So it sort of underlies how all research in the overall agenda will be approached. The second category I'm going to mention, social dimensions, which is the blue circle to the right here, includes 4 clusters of questions about public perception and engagement, political and economic dynamics, governance, and ethics. And then finally, the category on impacts and technical dimensions, which is this green circle where I've put a red box around it, contains 5 clusters of research questions that are probably of most interest to this audience, 4 of which I could see certainly include a role for NASA. So for example, the atmospheric processes cluster, which is the first one listed within this box, focuses on questions around the chemical and physical processes that produce the radiative effects of solar geoengineering. And this would include research activities ranging from high resolution simulations to observational, laboratory, and potentially outdoor experiments. Or for example, we have another cluster on what we call other impacts of solar geoengineering, which would focus on assessment of environmental and societal impacts of solar geoengineering proposals, and involve research to sort of develop detailed understanding of solar geoengineering effects on a broad range of climatic and biogeochemical variables, and which would include sort of observational elements. I'll note that the final cluster in this area, technology development and assessment, is an area that the committee specifically identified for a lower level of investment at early stages until we find out more about whether technology development in this area makes sense. Next slide, please. I just want to say a couple of quick things that the committee recommended about the possibility of outdoor experiments, including that experiments which involve releasing substances into the atmosphere should only be considered when they can really provide critical observations that aren't available or aren't likely to become available through other scientific processes like laboratory studies, modeling, or experiments of opportunity, being observations of volcanic eruptions or ship tracks, things like that. We also agreed that all outdoor experiments should be subject to governance, as well as making some specific recommendations about the quantities of material that experiments should be limited to for now. Next slide. Finally, we made recommendations about funding for a US program. That first basically emphasizes, as I said before, that funding on solar geoengineering should be a small component of overall global change research for now. And we recommended a budget of between $100 to $200 million over the first 5 years, which would be split equitably, not necessarily equally, but equitably among all research clusters, and should accommodate major field campaigns. Okay, I think next slide I'll end with just a few concluding thoughts, which is that the committee was in complete agreement that solar geoengineering cannot be studied in isolation. We see this program that we've recommended, the role of it is to assess not just technical feasibility of solar geoengineering, but also social feasibility. We highlighted that a research program could just as easily indicate that solar geoengineering should not be considered further, just as much as it could indicate that some further investigation is merited. Okay, next slide. So that's it for now. Thanks again for letting me present our findings to you, and the report is available online. Please check it out if you're interested.
Thank you so much, Dr. Ricke. And as you've said in our preparation, you're representing the views that were the consensus on the committee. And so thank you so much for providing this to us today. And we're so glad you could share direct from the committee to us. And now we're doing wonderfully on time. And so we have about 10 minutes to hear, particularly from Dr. Keith, who has active research in this area and has experience both on asking what are the opportunities with solar geoengineering, as well as what are the concerns, what are possible societal implications, and some of those unintended consequences we heard about. Dr. Keith, I'd love to welcome you now to share for about 10 minutes on your findings from years of work in this area, as well as teaching and sharing. Please go ahead.
Thanks very much. It's really a pleasure to be here. I'll do two things. First, I'll make a case for research on this. It's a little different, complementary to what Kate said. And second, provide some thoughts on the role for NASA, which I think is quite large. So my kind of boiled down case for research is focusing on stratospheric aerosols, although the other technologies are very relevant, is there is strong evidence that with stratospheric aerosols, one could arrange a distribution that was relatively even, north to south and east to west. This would need an observe, model, adjust feedback loop. You'd probably go for kind of hemispheric balance and roughly flat equator to pole gradient. And I think that the confidence that it's possible to do that, my view is that that's reasonably high. If you're talking about relatively small amounts of radiative forcing, a watt per square meter or so. All climate models that have been exercised, and really that is now all models and really hundreds of papers with aerosol perturbations like this or with proxies for those perturbations, show that doing this would reduce temperatures and extreme temperatures and would reduce other climate hazards as well. And there's evidence, at least for temperatures, that wouldn't make any regions, significant regions, worse off. At the same time, there's amazing amount of new data in the last decade or so, decade and a half, that shows that temperature is more important than we used to think for driving climate impacts. Obviously, mortality and morbidity, temperature, high heat waves kill people, but much more than that. It turns out that high temperatures make people learn less in school. So for example, the effect of a hot year or hot day on the day you take the test can be roughly as big as the effect of going between a kind of bad and good teacher in terms of the spread of outcomes. It's really a big effect. There are big economic effects of high temperatures. The net effect, in fact, on a paper that Kate was the author of, the only paper that's tried to actually quantitatively look at the impact on global inequality, income inequality, suggests that solar geoengineering might significantly reduce global income inequality, because basically the benefits of reduced temperatures, which are really quite robustly understood benefits, go most to people in the global south where it's hot. And I think that's really an important fact. Second, there's a lot of debate about this with some very prominent people, mostly people in the north who are relatively wealthy, arguing that it's unethical to consider this technology. They may be right, they have arguments. But to the extent that we know what regular people think, there's evidence from the papers that have done that, only a couple, that people in more vulnerable countries take this technology more seriously, both climate negotiators and regular citizens. And so I think that's kind of an important ethical reason to take this seriously as a way to manage the risks to some of the most vulnerable. And my kind of bottom line is that there's a real possibility, not knowledge, not confidence, but a possibility that emissions cuts combined with solar geoengineering might have less, perhaps significantly less risk than emissions cuts alone. To be clear, nothing about solar geoengineering changes the fact that we have to cut emissions to zero. The issue is, do we do more than one thing? And the reality is most complicated problems are solved by not just a single thing, but by a range of things. It used to be that people opposed any work on adaptation. Indeed, some people who now oppose work on solar geoengineering, like Al Gore, used to oppose work on climate adaptation. My view is that the reality is we need to consider a range of options. And I think it is, at this point, too early to say conclusively whether it would make any sense to do solar geoengineering or to forbid it for all time. I think what we can say, and this is what that committee said, is that doing some real research would make sense to reduce uncertainty and inform the future. Let me say a little bit about what NASA could do. I think there's a lot. First of all, there's a whole topic completely outside the scope of that NAS panel. So it wasn't that it wasn't important, they just wasn't in their scope, which is the possibility of space-based solar geoengineering. Now, this is something that I don't take that seriously because it has some tinge of science fiction, but it's not crazy. And remember, we're talking about something that would happen over a century or a century and a half. And on that time scale, I think we should take the idea of space-based solar geoengineering seriously. This idea has been around for a long time. There's actually an early paper by somebody called Early. And in 2019, we at Harvard decided to run a meeting really spurred on by Pete Worden, who used to run NASA Ames and ran one of the first important solar geoengineering meetings at NASA Ames a long time ago. Big range of people with public policy experience and space experience, SpaceX, Esther Dyson, Oliver Morton, a range of people. The meeting report is available on the Harvard program website. And that meeting concluded that it was really interesting to have more serious effort on space-based solar geoengineering. Interesting because it's very complementary in all sorts of ways to the work on terrestrial solar geoengineering. We concluded that the Lagrange point L1 options were the only ones that made sense, not LEO, low Earth orbit options. There's an immense amount of interesting work on development of space-based manufacturing, analysis of new ideas like dust shepherding, perhaps electromagnetic dust shepherding. There's also really interesting questions about governance. One of the central challenges of solar geoengineering terrestrially is that we have no governance architecture. Obviously, treaties don't magically mean good governance, but the Outer Space Treaty is quite wonderful. Its opening sentences make it very clear how outer space is to be governed and actually make it clear this to be governed with special attention paid to the poor and more vulnerable on this planet. And that's kind of an important thing that we have the Outer Space Treaty to provide a governance framework in a way we don't for other things. Moving down from space to the Earth, there is one of the technology we know most about is stratospheric aerosols, and that's one where NASA really has a special role. NASA has a special formal role through ozone assessment, but NASA also has some of the key observational platforms, and we desperately need new observations and new platforms. So NASA currently operates both the WB-57 and ER-2 aircraft. Those are aging. I've flown experiments on the ER-2. It's an amazing aircraft, but there's lots of room for new platforms. High altitude pseudo satellites. There's a bunch of work out of Ames, Swift Hail out of Ames. There's whatever happens as Google transfers its Loon program into public hands. It's clear that they got durations of close to a year, and they actually, towards the end of the program, worked on heavier payloads beyond 100 kilos. I think there's lots to do there. There's also a range of new space-based opportunities. So example, to go back to earlier speaker on this panel, Ball Aerospace is developing a really nice 3U limb sounder instrument. And I think if one was even remotely contemplating stratospheric solar geoengineering, you would want to have much better ability to determine stratospheric aerosols. That means both a global distribution of aerosols, trying to infer size distribution, and in situ observations that allow you to understand aerosol chemistry. I think the crucial thing is that we can't do this just by modeling alone. When we go out to nature, we continually learn new things. We're surprised. Our models are never right, and the models are always built on previous observations. So just to pick an example, almost all the models that have been used for looking at stratospheric aerosols, and the big aerosol people have thought a lot about has been sulfate aerosol, almost all those models assume that the aerosols in the lower atmosphere are basically all sulfates. That's almost certainly not true. There's a bunch of really interesting new data. Some that came out of the W57 from NOAA-led campaigns that make it clear there's much more secondary organics than we thought, especially in the lower stratosphere. That changes the optical properties of those aerosols. And so, you know, the models that have been published on solar geoengineering all basically would have a bias because they all include pure sulfate, and at least I think they all include pure sulfate. Maybe somebody will point me out, be wrong, but they mostly do. And that's quite certainly not what's there. And that's just one of the many examples of how we actually have to go out in the stratosphere, for example, and measure what's happening. Kate mentioned cirrus thinning. For cirrus thinning, the big question is really about observations of what fraction of cirrus clouds are or are not heterogeneously nucleated. And that's something that there's a range of remote sensing plus in situ observations, including really innovative new in situ observations that are very much things that the NASA community could participate in. So thanks a lot. Really look forward to the questions.
What a rich discussion. I'm so thankful for all the preparation you all brought to this discussion. Wonderful opening comments. And we have about 20 minutes left, a little less. And the time we have, I want to basically loop back around to everybody and let you respond to what you've heard from your other panelists. We'll save about the last 10 minutes for time and receive questions from the audience. So if you do have questions, please use the online system, and our wonderful team behind the scenes will channel those questions to us. You can start preparing your questions now. But for now, I'd like to actually go back to our starting point with Dr. Walsh and ask you to respond to all the great sharing we've heard from our colleagues, particularly on solar geoengineering or the importance for mitigation, and reflect on two angles. One is your role as an oceanographer, and the other is your role as someone who works across different countries and hears points of view from different countries. Can you respond to what you've heard with those two kind of roles in mind?
Thanks, Danielle, and thanks, everybody. Those are really great insights, and being somewhat new to the conversation, it's been helpful to hear. So I think in terms of oceanography, you know, I can't help but think of, you know, what ramifications it has for ecosystems on so many different levels. So there's a lot that we could dive into there, but that's a long conversation probably. I think I also can't help but think, especially when talking about stratospheric atmospheric injection, I guess that would really be a global process, and getting global agreement, I think I could see being really challenging. You know, I know even getting agreement at a national scale around the world is difficult. So, you know, I think obviously we've been successful, as you pointed out, sort of space agreements, but I do, you know, see the challenges. Some people may see the benefits of solar and geoengineering, but others may be more concerned about the challenges, and or, you know, may be perfectly happy with their warmer conditions. So I think there's a lot of aspects to consider, but thanks for all those thoughts, and I'm look forward to hearing more conversation.
And just to push a bit, since you highlighted this reference to possible impacts on the oceans, is it possible just to outline, without going into so much detail, some of the categories of concerns that you thought of in terms of impacts on ocean ecosystems?
Yeah, I mean, I guess there's, you know, you've talked about 3 different methods, so they all have their own aspects. But, you know, at first, the base of the food web, phytoplankton, what sources of light they're using, and how, if you manipulate it at a global scale, you know, I think the hope is that would maybe reduce production in a global way, somehow uniformly, I'm not sure. And then I think locally is where, yeah, I'm sure there's questions. And then at the local scale, boy, there's a lot of questions on how, sort of so many different ways in which production, which is just, the foundation of the food web. So David, sorry.
I mean, the hope is certainly not that it would reduce production. I think the answer is we don't have enough knowledge, but the hope is it would increase production. Pretty much all the models now have been for quite a long time, that the global ecosystem model suggests that it would increase global primary productivity, small amounts of solar geo. And in fact, I have a paper with a lot of colleagues. I'm a minor author coming out in a week and a half or so in Nature Food that does one of the cleanest versions with probably one of the best crop models embedded in a state-of-the-art GCM that shows that it would be remarkably effective, and indeed more effective than CO2 cuts in protecting global agricultural yields. So that may or may not be true, but that's what the evidence suggests. And I know that one naturally thinks if you're reducing some sunlight that you're going to reduce productivity, but of course, you're talking about sunlight reductions of order 1%, and you're talking about also changes in temperature, which impact yields, as well as changes in water vapor that impact yields. And so you get this net effect that does appear to be increasing yields.
Yeah, well, and to that question though, nutrients are often the limiting phenomenon for production. So I'm curious how sunlight affects the cycling at many scales. Any thoughts
Right
there?
question. And that's where ecosystem experiments are needed, for sure. That's where there just hasn't been enough really looking at impacts. There's lots you could do on ecosystem level experimentation.
That was a very interesting conversation. Thank you for that back and forth. This is the kind of question, because what stood out to me actually, both from Dr. Ricke's presentation and Dr. Keith, was particular areas where we know there's scientific uncertainty, where there's opportunities. And I was struck by the idea, well, there's experiments we could try, and then there's observations of opportunity. And maybe one question to explore with all of you who want to comment, are we already collecting all the data available from the observations of opportunity that are available, such as volcanic eruptions, the behavior of planes? Are we missing those as they kind of pass through, or are we collecting them because our existing systems already cover them? I guess Dr. Ricke, but also Dr. Keith, do you have comments on whether we could just immediately start by collecting more of the existing natural experiments?
I can comment on this briefly, and I know that David probably has something to say as well. This is something that we highlight in our report as the opportunity to make better use of experiments of opportunity, because of course there is some existing scientific infrastructure for making observations after something like a large volcanic eruption. And of course we have observations of ship tracks that have already been exploited for understanding questions around marine cloud brightening. However, a lot of the instruments and things weren't designed with questions of the effectiveness of solar geoengineering in mind, right? And the questions that we ask about solar geoengineering might be slightly different than the ones that these instruments were intended or campaigns were intended to address. And so part of what we do in the research agenda recommendations we make in our report is think about how you may be able to build upon existing research efforts or make plans for future ones with these types of questions in mind, building upon already existing parts of global change research.
Yeah, strong agreement. I think there's lots to do, but I think the point is it won't happen without some level of problem-focused investigation. It's not that you necessarily need to do that much more than in terms of new science, but what you need to do is apply the science and observations we have across atmospheric and earth sciences to this problem. And that's my hope, is that following the committee, there'll be more willingness in the research enterprise to do that. Because just to be blunt, what's happened here is this idea is not new, it's been around forever, but there's been really strong disagreements about whether research even makes sense. With, to be clear, to the extent that we actually have done any kind of polling of what scientists think, it's pretty clear that significant fraction of, say, IPCC authors think the research makes sense. But nevertheless, there isn't actually any kind of national research program. And that's the kind of thing that I think this committee is formally advocating, that I think would be very healthy. And to be clear, research does not mean we move to implementation. So let me add one more thing. There was research on a very different kind of geoengineering called ocean iron fertilization. And that research pretty clearly showed that the method basically doesn't work. There's lots more you could say, but big picture, it really doesn't do what you'd want. And interest in that is pretty much waned. And that's a pretty good example that you can do research on something and there's not an automatic slippery slope to deployment.
That's a very helpful historical perspective. I want to bring in Dr. Hakimdavar for a moment and ask, given what you heard from the other panelists and your broader reflections, do you have additional examples to share or additional insights on opportunities for some of the missions that you know about or missions that you think could be proposed in the pipeline through private sector collaboration with public sector that could respond to some of these scientific uncertainties?
Yeah, sure. Well, David, I know you've talked to colleagues in the past, so certainly there are already some ideas out there. First, I actually just wanted to reflect a little bit on what JP said around the unintended consequences. And I think that's where the challenge and the fear is. And we have examples of this. I mean, I mentioned I'm coming from the Department of Agriculture, Forest Service, and there are a number of examples of unintended consequences from actions that were taken to address some of our land management challenges. So at the same time, what I really like, Kate, is how you presented, and in the report as well, but in your presentation, that they're doing these controlled experiments and utilizing existing information and doing this in a responsible way. There is an opportunity for research. I think having more tools in our toolbox is a good thing. And I'm I guess in a way just sharing my personal view as a scientist reflecting on this. And in terms of, one thing I did want to mention, and I just noted down, was the stage 3 instrument, which is currently on the International Space Station. That's measuring stratospheric aerosols. And another one I didn't hear, David, you mentioned that, but Ball did contribute to that as well. And I think, it connects with some of the other technology that I think you had talked to my colleagues on with the solar occultation instrumentation. So yeah, I mean, certainly I think there are definitely opportunities for us to look into our existing or potential capabilities on the technology side and the engineering side. But again, maybe going back to the scientist side of my brain, I would love to see those opportunities kind of also help us in opportunities for additional data collection, let's say additional observations, also help us with other aspects of climate change that we talked about earlier on in terms of the information that can support mitigation and adaptation efforts. And I think that would be a real kind of win-win to utilize, make the most out of the investment, right? And make the most out of the funds that you are requesting for the research program.
I agree, but I think it's important to bear in mind this is really about a risk-risk trade-off. So completely agree about unintended consequences and surprises are guaranteed. There's no version, as Kate very well said, no matter how much research is done, there will be big uncertainties left. But remember also that even if we eliminate emissions tomorrow, the climate risks are very real. Speaking of kind of vulnerable communities, about a year and a few months ago, I spent time in Bangladesh where I was invited to talk about this with senior leaders and also went to talk to local people in coastal communities. And the impacts are very large in the Bangladeshi Delta, and they will be there even if emissions are eliminated tomorrow. And given that we really have significant models that suggest you could substantially reduce impacts by these methods, my view is you got to take it seriously. Even though there will no doubt be risks from the methods, the benefits to some of the most vulnerable might be quite large, and that's why we need to really think about it hard.
That gives me a question. I was wondering people's response to Raha's question to ask, is there a technical synergy between the kinds of observations you want to make for what might be called traditional mitigation that focus on reducing emissions and the kind of observation we want to make to further the research agenda? Because we highlighted just now that maybe some of our traditional methods for observation aren't tuned to answer just the particular science questions. For those who have thoughts, do you see that we could easily, like very affordably, start to measure at the same time some of the kind of current things like understanding the overall sort of air quality impacts on due to aviation, at the same time kind of get more information that would help with understanding this solar geoengineering path? Are they close enough, or do we have to actually have separate observational approaches?
Well, the main core of traditional mitigation is that we've got to cut CO2 emissions. We sometimes get these conversations of sustainability to talk about everything, but the central issue is decarbonizing the industrial economy. And for that, observations aren't really the issue. The issue is implementing technology and the political will to do so. But there certainly are overlaps. And one really interesting one that is one of these shady areas where it's not quite clear if it's geoengineering or not is commercial aircraft contrails are somewhat cooling when they occur during the day and somewhat warming when they occur during the night. And there's a lot more we can learn about what makes those contrails, but there's also at least some possibility for adjusting aircraft flight tracks or altitudes slightly through a kind of optimal programming algorithm where you'd be trading off a little extra fuel burn for a little extra cooling. Several people are looking at this now, and that's very much something that's like at the intersection of aviation industry, carbon offsets and observations. And that's an example of something that really might be interdisciplinary in a kind of cool way.
Thanks for that highlight. I want to appreciate a colleague here at MIT, Professor Stephen Barrett, who has recently shared with our faculty community some of his work in this question of could we literally give different flight patterns to planes and have them respond in a way that would be contributing to reducing emissions. So thank you for mentioning that. It's a great example.
Yeah, I've collaborated with Steve. That's how I think about it.
Others comments on either the opportunities or sometimes the challenges actually of sort of thinking about multiple kinds of observations at once?
Yeah, I guess I wanted to comment and just applaud the report for recognizing the value of transdisciplinary research and really thinking about the social side. As David pointed out, I mean, implementation of mitigation is already a major challenge, and that's for a problem that we know of and with options available. I don't know, for something like solar geoengineering, implementation is going to be maybe have even bigger hurdles. There are so something to really think about, and this is for adaptation approaches and mitigation approaches. We really need to be doing transdisciplinary research, and what we mean by that is engaging people at a variety of levels through the process. I'm currently working on a project funded by the Belmont Forum, which you might be familiar, which focuses on transdisciplinary work on multi-use of the ocean involving numerous countries. And it's been an exciting process. It's got challenges, it's slow, but it's important. And I want to emphasize that.
This is great. I think we have time in our last few minutes for one or two questions from the audience. And with that, I'll invite.
Could I just weigh in really quickly on that?
Sure, go ahead. Please, Kate.
Sure. Yeah, no, I can't agree more. And, I didn't have a lot of time to talk about our recommendations about transdisciplinary research, but this was something that the committee really agreed on, and something that in my own work, I think is important as well, because there's a lot of important reasons why we need more input from the public and practitioners at early stages in the research process around solar geoengineering in particular, but also other areas of climate change research that have not to just to do, in our report, we talk about the ethical reasons for this, but there are also substantive reasons as well, right? That studies show that input from diverse participants and practitioners improves research. And also, in particular for solar geoengineering, this is important for legitimacy, because basically, if people feel detached or skeptical of the research results because of who's doing the research, that research ultimately won't be actionable because it won't be perceived as legitimate. And that's why it's particularly important for solar geoengineering that this research program that we develop is transdisciplinary.
Well said. We'll now invite Jim back on, who will speak the questions from the audience.
Great, thanks, Danielle. So this one's interesting, and it was kind of something I was thinking about too. Was so what might be the potential criteria and needed measurements to help the community decide whether or not to implement any of these solar geoengineering options? Basically, what I was thinking in a more simple term is the 80-20 rule. When do we have enough, to prevent analysis paralysis? When do we have enough information to go ahead and try something? And when will the community feel secure in that knowledge?
Thank you. I think our responses will be our final words on the topic today. We have about 2 minutes left, so let me invite everyone to comment briefly if you'd like to, but I'll start with David.
Sure. I think the answer is different communities around the world will have very different feelings about when implementation might make sense. So I think you're asking, that's essentially the crucial question. I think one of the scary things about this technology is that some crude versions of it could basically be implemented with no new development or science. I don't think that's a good thing, to be clear. I think it should be opposed, but I think that's a plausible outcome. And I think one of the worries is that as risks grow, especially to some of the most vulnerable nations, there'll be increasingly pressure to do desperate things. So my view is that there's no way to know when is enough information. And for some groups, they'll never feel it's enough information. For other groups, they may feel it too early. Our job in the research community is not to decide what happens. Our job in the research community is just to provide good, unbiased advice.
Thank you, David. I'll ask Kate to give closing comments and feel free to respond to the question.
Sure. I mean, a little bit of what I'll say is perhaps my own take as opposed to the committee, just because I'm responding on the fly. But I think part of this will just have to do with how quickly and the volume of research we end up doing and how it compares to the research we do on climate change. I mean, if you look into climate change impacts research, so for example, studies that have been done on the agricultural impacts of greenhouse gas driven climate change. If you type that into Google Scholar, you'll find, 3 million studies coming up, right? Whereas, the types of studies that David just mentioned, the one that he has coming out, I'm sure it's an excellent study, right? But if you do the same for agricultural impacts of solar geoengineering, you'll find 5 studies, right? And the problem is that right now, in the presence of this huge asymmetry in information availability about the impacts of climate change versus the impacts of solar geoengineering, you really can't do the sort of risk comparisons that are required because there hasn't been the stress testing of the results we have about solar geoengineering's effects and impacts yet. And so at minimum, I don't think we'll have enough until we can do that kind of stress testing and the research community and the body of research has expanded.
Thank you so much, Kate. We just have a few seconds left, but I want to just give a chance for JP and then Raha to make very short closing thoughts on the entire discussion. So JP, just a few seconds.
Yeah, I'll just reiterate that I think that in every community's and country is going to have a different perspective on what works for them, as David said. And I think just involving people in the process throughout the process from beginning to end is going to be important. Some may want to start going tomorrow. So we'll have to provide science and that will help. Thanks.
Thank you so much. And Raha, final words.
Yeah, I will just add to that, underlining the point that JP made about how good it is that there is that the committee is advocating for interdisciplinary collaboration and research to happen simultaneously. That's really important. So it's still, at the end of the day, it is research, but that will bring different perspectives into this conversation and this area of ongoing work. So yeah, kudos on that. And I think that is important to really underline that and push that moving forward. And of course, opportunities for the technology developments are certainly there and can, again, just taking the opportunity to connect what's being used in this research to the greater climate change challenges. And so multi-purpose would be excellent. Yeah, thanks.
Thank you all so much. And a big thanks to our host, to AAS, as well as to Goddard and to all the organizers. Wonderful to discuss this with you today. And we'll close for now. Thank you.
Excellent. Danielle, thank you so much. Kate, JP, David, Raha, thank you so much. That was excellent. Really good. And thank you very much to Teledyne Brown Engineering for sponsoring that session. We really appreciate it. We will now move directly into our next session. Please click on the link to head to Hitching a Ride, Commercial Human Spaceflight, Enabling Research and Science.